Hi, I am Souraja. Today I am going to present the paper Optimal Baseline Corrections for Off-Policy Contextual Bandits by Gupta et al. On behalf of my team consisting of me, Khushi and Thanish. Recommendation systems or general ranking applications can be modeled as a reinforcement learning problem where the context typically describes the user features, the actions are the items to recommend, and the rewards can be any type of interactions logged in the platform between the user and the item. Contextual mandate is a specific type of reinforcement learning problem where, given a context, the learning agent learns to take an appropriate action to optimize the immediate reward instead of considering both the immediate and future rewards. The general contextual mandate or the so-called on-policy contextual mandate problem can be modeled as learning a policy. A policy is basically a strategy or a mapping from states to actions that an agent has to follow to maximize the rewards in an environment. The policy can be mathematically defined as a conditional probability pi of taking an action A given a context X. So the value of the policy V pi can be defined as the expected reward. The expectation is taken over all possible actions A and all possible context X. Our task is to maximize the expected reward or the value of the policy V pi. So we will follow the gradient ascent algorithm where the parameter theta of policy pi is updated according to this equation theta t plus 1 equals to theta t plus eta is the learning rate and the gradient of the estimate, the V pi. So after applying the well-known reinforced log tree, we can get the expression for the gradient of V pi as this equation given down below. We can see that this estimate of the gradient of V pi or the expected reward is unbiased. But because of the high variance of the reward R, this also has a high variance. Our target is to reduce the variance of the expected reward. There are different policies to reduce the variance, and control variates is a well-known method to reduce the variance of this estimate. Control variate is basically a random variable with a known expectation, which is somehow correlated with the original estimate, in our case V pi, and thus we can reduce the variance of the estimator without adding any extra bias using this control variate. This control variate can be additive or multiplicative. Additive control variates subtract something called a baseline from the reward while ensuring that the expected value remains unbiased. The additive control variates can be baseline corrections, doubly robust estimators, or regression adjustments. On the other hand, the multiplicative control variates basically multiply a control variate with the reward to reduce the variance while keeping the bias same. And the multiplicative control variate methods are like the self-normalized importance sampling method or SNIPS. Under additive control variates, baseline corrections are a well-known variance reduction method where we have to find out the optimal value of the baseline beta, which is subtracted from the reward R, which can also minimize the gradient of this variance estimate. So by following the general derivation for the Markov decision process, we can find out the optimal value of beta for on-policy contextual bandits. In on-policy learning, deploying the policy pi is a costly as well as risky prerequisite for estimating V pi, and hence comes the off-policy learning approach, where an agent learns a policy called the target policy pi by using data collected from a different policy, which is called the behavior policy pi naught. The expectation V pi can be unbiasedly estimated using samples from this different policy pi naught through importance sampling, also known as inverse propensity score weighting or the IPS weighting. The weights, the importance weights is a ratio of the two policies, pi of a given x divided by pi naught a given x. This method adjusts for the difference between the behavior and target policies. Or the difference in probabilities between pi naught and pi. For a dataset D of logged contexts, actions, and rewards collected under policy pi naught, The inverse propensity score or IPS estimator for V pi is given as the second equation, which is a weighted sum of all the rewards, and the weight or the importance weight is pi of a given x divided by pi not a given x. And for importance sampling to work correctly, the common support assumption must hold. That is, for every action A and context X, both the numerator and the denominator of importance weight should be positive. The estimator is maximized by gradient-based optimization. The gradient of the estimator is calculated using Monte Carlo approximation. For a mini batch B of data, the gradient of VIPS is given by the last equation on the slide. Importance sampling often leads to very high variance compared to on-policy estimators, and that's why there are several variance reduction techniques which don't add any extra bias but reduce the variance. These offline estimators are self-normalized importance sampling and doubly robust estimations. This paper shows that these off-policy estimation techniques perform equivalent optimization as the baseline corrected estimation. So baseline corrected estimators are generally used in on-policy estimations, but this paper uses it to unify all other off-policy estimators and calls it the offline estimator beta IPS. In baseline corrected estimator, beta is a baseline control variate that is subtracted from each reward and added back to the final estimate, ensuring the unbiasedness of the estimator but reducing the variance. If we take an expectation in the first equation of the slide, then we can get that expectation of V beta IPS equals to V pi. A brief description of the other offline estimators which this beta IPS method unifies. The first one is the self-normalized importance sampling, which uses a multiplicative control variate to rescale VIPS, and the scaling factor is an asymptotically unbiased and parameter-free self-normalizing IPS or SNIPS estimator, which is nothing but the summation over all the importance weights. Importance weights means that pi of a given x divided by pi not a given x. So Joachim et al. Showed that optimizing VS and IPS is can be reframed as an optimization task using the Lagrange multiplier method, where we have to optimize VIPS with a shifted reward. This approach of translating the reward by a tunable hyperparameter lambda is called the bandit net. And the other off-policy estimator is called doubly robust estimation, which reduces the variance of VIPS by using a regression model of the reward R cap. The name derives from the fact that it is unbiased if either the logging parameter pi naught or the reward model R cap is unbiased. In doubly robust estimation, the regression model of reward R cap can also be treated as a single hyperparameter. So we can say that the beta of baseline correction, the lambda of self-normalization, and the R cap of doubly robust estimation all are equivalent. So this paper focuses on finding out the optimal baseline beta because it will be at least as optimal as any estimator in the underlying families of offline estimators like this SNIPS or this doubly robust estimator. This paper gives a formal proof of finding the beta by minimizing the gradient variance, which is this equation. And it shows that among all the families of gradient estimators with a global additive control variate like the beta IPS, bandit net, or doubly robust estimation, the beta IPS method using this value of beta will have the minimal gradient variance. Also, this paper tries to find out the optimal beta by minimizing the estimation variance. And it shows that by using this value of beta in the beta IPS model, one can get the minimum mean squared error. In order to evaluate the off-policy learning and off-policy evaluation methods, the authors have used Open Bandit pipeline, which simulates a generic offline contextual bandit setup, but there is a strong correspondence to the real-world recommendation scenarios. There are two learning setups. One is the full batch mode, which optimizes beta IPS with the estimator variance minimizing baseline, and another is the mini batch mode, which optimizes beta IPS with gradient variance minimizing baseline. The results for the full batch training in terms of off-policy learning shows that beta IPS converges much faster to a substantially greater learning policy value compared to SN IPS or the traditional IPS. It is because of the high variance of the IPS. And in the mini-batch setting, the focus is more on minimizing the variance of the gradient estimate, unlike the full batch mode, where the focus is more on reducing the variance of the estimated value. In mini-batch setting also, the equivalent results are found uh, compared to full batch setting, where beta IPS achieved higher policy value compared to IPS and bandit net. And also beta IPS showed the lowest gradient variance among all. Off-policy evaluation result shows that beta IPS method showed the lowest mean squared error MSC compared to IPS, doubly robust, or SN IPS in simulated settings. Also on Zozotown logs, which is basically real-world recommender system log, beta IPS again showed the lowest relative error among all the other estimators and also sometimes the lowest empirical variance. In summary, the additive baseline corrected off-policy estimator unifies all the other off-policy estimators like traditional IPS, SN IPS, or doubly robust estimators. And the proposed value of the optimal beta can reduce the variance in the estimated policy as well as the empirical gradient. The experimental results show that beta IPS surpasses the performance of the other off-policy estimators in terms of off-policy evaluation and learning both. The future work suggested by this paper is to extend the approach to offline reinforcement learning, and they also want to adopt this method for ranking applications. Thank you.